Today we're going to take a look at a problem from the 2025 IMO Shortlist. The shortlist is basically a selection of 7 to 8 problems from algebra, geometry, number theory, and combinatorics. Um, the kind of the best problems from the long list, of which 6 got chosen to become the final IMO problems. And their difficulty ranges from, for example, for algebra, you have A1 through A8. Sometimes it's 7. Um, and so 1 is easiest and 8 is hardest. Um, and this shortlist gets kept secret for a year, up to the next IMO's closing, and it is used for the selection of national teams. So it's a fairly secretive shortlist, and the problems from it are all very interesting. Basically, IMO level problems. So this is A2 from 2025, from China. Basically, it asks the sunshine cost is this expression for a sequence of 100 integers as I and j vary over these numbers. And we want the smallest possible sunshine cost over all sequences of pairwise distinct integers. So first of all, I would like to introduce the notation of what we call a prefix sum, which is basically exactly what this thing is. It's basically the sum from A1 through AI. So especially we have P1 is equal to A1, P2 is equal to A1 plus A2, and so on, all the way to Pn. Pn would just be this, P100 would just be the sum of everything. Okay, now suppose we have written down A1, A2, all the way to A100, and then we have the prefix sums P1, P2, P3, all the way to P100. What's going to happen is I'm going to choose a j, index j for the sequence A, and an index I for sequence P, and I'm going to take their difference, and I want this difference to be maximized. If we plot the A's and P's on a number line, so let's say the red points are A and the blue points are P, then I basically want to pick a red and a blue such that their difference is maximized. And it's very easy to see that the maximum difference comes from choosing the smallest A and largest P, or the largest A and smallest P. So mathematically, if we have sunshine cost S, then it is the maximum of P max minus A min and A max minus P min. So let me explain some of this. So first of all, P max is basically is this point, right? Minus A min. So this is a candidate difference. And this is also a candidate difference. Now, there's two things I need to explain about this equation right over here. So first of all, why can't this be negative, right? And the answer actually lies here. P1 is equal to A1, which means that actually, if you consider the interval of A min to A max and the interval of P min to P max, these intervals actually overlap, and they overlap exactly at P1 equals A1. So this is P1 equals A1. And the reason is A1 is A1 is between this interval, and P1 is between this interval. And so therefore, they share at least this one point. And that means that P max is greater or equal to P1, which is equal to A1, which is greater or equal to A min. So this is at least 0. And this is, by the same reasoning, also at least 0. Now, it remains to show that S is indeed the largest possible difference as given by the statement. And the way we're going to do this is by considering any a choice of PI and AJ, and we wish to show that this difference is always at most S. And whenever we have absolute values, it's always nice to do some casework. We can do case one is PI is at least AJ, and this means that the blue point that we chose is to the right of the A point that we chose. And what we're going to do is we're just going to move this to the left and move this to the right. So it's very clear that since we have A min is less than or equal to AJ, and we have P max is greater or equal to PJ, is greater or equal to PJ, we know that P max minus A min is greater or equal to PJ minus A oh, sorry, I wrote pi, is greater or equal to pi minus aj. Um, pi minus aj is just this generic pi minus aj absolute value. Um, since pi is greater or equal to aj, and this is less than or equal to s. So we have shown s is greater or equal to um, basically all pi greater or equal to aj. Um, so basically, we have shown like this statement for all in this case. Then case two is when pi is less than aj. And in this case, we have I here and j here. And I just need to shift this to the left and this to the right. So I know that a max is greater or equal to aj, and p min is less than or equal to pi. And I can repeat the exact same argument that s is greater or equal to, sorry, a max minus p min is greater or equal to the absolute value of pi minus aj, right? And this would just be inverted. Like this term would just be inverted down here. So I have shown this quite rigorously, but like intuitively, this is very, very easy to see, this expression right over here. So this is what we're gonna move on with. So S is equal to the maximum. So this is the sunshine cost, right? So this is the expression for S. P max minus A min and A max minus P min. So it is the maximum of these two things. Okay, now we're gonna let C be the smallest possible S over all sequences AI. As required by the statement. Now, you can just play around with a lot of sequences, but I think it's not really so. Try to construct a sequence that really minimizes this S. And I think it's not hard to see a sequence like this right over here. So what we're going to do is intuitively, you want to keep the span of everything here as small as possible. So you actually want negatives and positives that cancel each other nicely and keep it very thin and like condensed. So what we're going to do is we're going to start with negative 25. We're going to jump up by 50, down by 50. We're going to jump up by 49, down by 49, all the way to jump up by 26, down by 26. Since I can't do 25, because I want to save the pair negative 25 and 25 for like here or like later. I'm just going to skip to 24. I'm just going to keep jumping around like that until I hit 1, negative 1. So now we've basically done 99 numbers. And the natural term to go back to is 25. So I'm just going to do 25. And if we have this as our sequence AI, we're going to find that um, A max is 50. Sorry, 50. A min is negative 50. P max is 25. P min is negative 25. So to visualize this, we basically, so if this is 0, we jump to negative 25, and then we jump to 25 by adding 50, and we go back, and we jump to 24 and back, and so on. We just keep jumping back and forth, always ending up back at negative 25. And then in the very end, at this 25, we be back at 0. So this is what the sequence looks like. And we have these numbers. And if you take this S over this, we have S is equal to 75. Now we hypothesize that this is the smallest possible S. So C, the smallest possible S over all sequences, because we already have S is equal to 75 for this particular sequence AI, we know that C, the smallest possible S, must be less than or equal to 75. So by showing this example, we already have this inequality. And this is something very typical in math Olympiads, where you use an example to show one side of the bound, and you use a proof to show the other. So now what remains now is to show that C is at least 75, which is basically the harder part of the proof. So moving back to this definition of S, we can notice that whenever we have a generic sequence like this of AI, it seems that it is easier to work with A max, A min together and P max, P min together. So this combination is actually not very friendly to us. So we would like to actually transform this expression right over here. So uh, we want to, so since C is the smallest possible S over all AI, we just need to show that, well, this is equivalent to showing that for all sequences AI, we have that S or the maximum. I'm just going to copy this down again because it's very helpful. A max minus P min. This guy is at least 75. Um, right? So basically, this is what we're trying to show. And if we show this, we're done with the problem. Um, this leads us, again, the observation before, we want to try to put these two together. And what we're going to do is we're just going to consider the expression P max minus P min plus A max minus A min. This, sorry, the terms marked in red, this thing right over here, and the terms in blue are this thing over here. Now, both of these are less than or equal to S because S is their maximum. So this thing is less than or equal to 2S. And if we can show that this is at least, because they're integers, if we can show that they're 149 or 150, then we're basically done. We have shown this and hence this. So what we're going to do is we're going to consider this now component by component, right? So basically we just did like a regrouping. Um, so let's first look at A max minus A min. The very obvious observation to make is that since there are 100 distinct AI, we know that A max minus A min is at least 99, right? Because they're distinct and they're integers. So even if you put them all together, you have that their difference is at least 99. You have like 100 consecutive integers. And that already brings us very close, right? So basically what remains to be shown is we wish to show that P max minus P min is within, is at least 50. Um, so how can we show something like this? Well, recall that for any I at least 2, AI is equal to PI minus PI minus 1 per like the definition of prefix sums. And what's really nice is that if we have any AI with I greater or equal to 2 that has absolute value greater or equal to 50, what we can do is, so for example, AI is positive, then we know that PI um, is less than or equal to P max, and we know that P I minus 1 is greater or equal to P min, then we know that subtracting 1 by 2 gives us P max minus P min is greater or equal to Pi minus Pi minus 1, which is equal to PAI. And since AI is positive and its absolute value is greater or equal to 50, we know this thing is greater or equal to 50, which is what we wish to show here. And if AI is negative, then I can just pretty much do the opposite. I'm just basically swapping PI and PI minus 1. Then I have P max minus P min is less than or equal to Pi minus 1. Is greater or equal to Pi minus 1 minus Pi, which is equal to negative AI. And like this means that AI is at least 50. this means that AI is within less than or equal to -25. So this would actually be greater or equal to 50 still. So like it's the exact same reasoning. So we basically just showed that whenever we have any number after um, so like any element with I greater or equal to 2 that has this, then we have the desired property of P max minus P min, which would later satisfy our overall inequality of this. So that is case one pretty automatically. And case two is when for all of these, we don't have uh, this, which basically means for all I greater or equal to 2, we have AI is within 49, or the absolute value is within 49. And since there are 99 numbers that span from -49 through 49, which are also 90 numbers, then we know that A2 all the way to A100 is a permutation of this sequence of numbers over here. Um, that means, does this help with this right over here? Well, what we actually did not look at yet is A1. And because all these numbers with absolute value less than or equal to 49 have been taken, we know that A1 has absolute value at least 50. So without loss of generality, log A1 is greater than 0. We can later easily cover A1's less than 0. So this basically means that A1 is at least 50. So what we have here is basically, if we have like a number line, we have 49 over here, -49 over here. We have a bunch of numbers here. We have some number here. Um, it seems that it would be really convenient if we could take, um, so again, we want to show this statement right over here. But let's not forget that um, we ultimately we still wish to show that C is at least 75, or actually, sorry, S is at least, we have S is at least 75. Um, and S is, again, the maximum possible difference. And what we're going to do is, this is kind of like the finishing touch. So S is the maximum difference um, uh, of Pi minus Aj. So what we can do is actually, we know that some Aj has -49. And nicely, we have P1 is equal to A1. Then we know that there exists some Pi, sorry, we know that P1 is at least 50, and this is, and some AJ is -49, which means we can take I is equal to 1 and AJ is equal to 49 to obtain a candidate difference that makes S is at least 50 minus -49 is equal to 99. So basically, for both cases, we have actually shown that. Um, let me go through the logic again. So this is quite a messy write-up, but um, like it's natural to first do a brainstorming like this, and then you can write down the proof formally. So, but like we already know, like mathematically, this is already correct. Basically, what happens is, again, we wanted to show. So after giving this example right over here, we wanted to show that C is greater or equal to 75, which is equivalent to showing that for every sequence, we have S is greater or equal to 75. So like this thing is what we were trying to prove. Um, and then we had case one where for I greater or equal to 2, we had some AI with absolute value greater or equal to 50. This led to P max minus P min is greater or equal to 50, which is this, which then later helped fulfill this. So this directly proved S is greater or equal to 50, and we have so sorry, like S is greater or equal to 75 for all sequences in case one. And in case two, through this magical argument, we also showed that for all sequences in case two, we have S is greater or equal to 75. And by having this, so basically we showed that in all cases, S is greater or equal to 75. Therefore, we know that C is at least 75, or like the smallest possible sunshine cost is 75. So therefore, we have shown both bounds. In the proof, you would directly start with the different cases. What I showed was the logic of how to get to this specific case. Um, and so for each case, you would have S is greater or equal to 75, and so therefore C is greater or equal to 75. And with the construction, C is less than or equal to 75, we know that C is equal to 75, and we know the construction. So that is this IMO problem, IMO shortlist problem, A2 of 2025. Thank you.